Hello everyone, my name is Aarohi and welcome back to my channel. So guys, so far we have understood the complete scaled dot product attention process in transformers. And before we start today's concept, let's first revise what all we have covered till now. And before we begin guys, a small request: if you find these videos helpful, then please like and share them because it really take lot of time and effort to create such detailed content. And also feel free to comment if you have any questions or suggestions. Now let's begin and let's see what all we have covered till now. So this was our input sentence. My name is Aarohi and I love coding. First, we used tokenizer and tokenizer converted this raw text into tokens, and these are the tokens. And then tokenizer performed the second job, which is to provide unique IDs, and these are the unique IDs provided to all these tokens by the tokenizer. After that, we used embedding layer. Embedding layer is used to get the embedding vector for each token. So for my token, this is the embedding vector. For name token, this is the embedding vector. And the size of embedding vector means how many values you are going to have in each embedding vector depends upon the size of D model. And let's say D model in our case is 512. So each vector have 512 values. After that, we performed positional encoding. Why we use positional encoding? Because we want to send the position of each token with the token embedding. So this is the token embedding and this is the position embedding. And then we performed element wise addition on these two. Once we perform the element wise addition, this is what we got. This is the input to the encoder. The size of this final vector is 8 into 512, means 8 rows you're going to have. So this is the matrix, right? So we have 8 rows over here and each row will have how many values? Numbers we are going to have in each row? 512 numbers. Why? Because the D model is 512. So this is the matrix. This matrix will be the input to the transformer encoder. Then the task of encoder is to know the relationship between the words, and for that encoder use query, key and value. And I've told you that you cannot calculate query, key and value directly. You need weight matrices for that, and I have explained you this example. So we used 3 weight matrices. WQ is the weight matrix used for query, WK is weight matrix for key, and this is the weight matrix for value. And using this formula, you'll multiply the weight matrix with the input. And what is the input? Input is a matrix of size 8 into 512. So for each token, for each query calculation, you will do this. So you can see over here. So suppose if you want to calculate the query of love token, then you will multiply the embedding of love token. So this embedding, so this was the embedding of love, so you will multiply the embedding of love token with the this weight matrix of query, and this weight matrix is initialized randomly and it learned during training, and we perform multiplication and we get this query, key and value. So guys, today I'm not going to discuss these things in detail because we have already covered these things, and if you don't know what these things are, you can check this lecture, okay? And guys, we have discussed about dk and dv also, and this is how you calculate dk. 512, which is D model, and this 8 is number of heads. This part we are going to discuss in some time. What is heads, why number of heads are 8, this part we'll discuss in some time. So if you will divide this by this and you'll get 64. It means each token's query and each token's key, you are going to have a vector, and that vector will have 64 values in it. And guys, after this step, we got query, key and value vector for each token. So for all the 8 tokens, we got query vector, key vector and value vector, and each vector have 64 numbers in it because dk is 64 and dv is also 64, means each value vector will have 64 values in it. So after this step, we have query, key and value vector for all the tokens which are there in our input sentence. So these are the tokens in our input sentence, these 8 tokens. So for all these tokens, we have query vector, key vector and value vector. Guys, after this step, still your encoder does not know the relationship between the words, means for which particular word, what all other words are important. So for that, you need to calculate the attention. So next step is to perform the dot product between query and key, and we are using key transpose. Why we are using this key transpose, guys? To know this, you can check this video over there. I've explained in detail that why we are using key transpose. Right now I'm just giving you a brief idea so that the inner dimension match. So that's why we use this key transpose, so that we can get a 8 by 8 matrix. So when you will multiply query of each token with keys of all the tokens, you will get a matrix of 8 by 8 like this. This is a attention matrix, and this attention matrix you got when you multiplied query and key transpose. So each row is a query and each column is a key. This is the query of my token, query of my token, and this is the key of my token, query of my token, and this is the key of name token, and then query of my token, this is the key of is token. What it means is, what these numbers means, higher number simply means that this query gives more attention to that particular token. The query of name token is giving more attention to Aarohi token, right? So this score tells us that this query gives attention to higher attention to which token and lowest attention to which token. So this is the attention matrix, and this is a 8 by 8 matrix, 8 rows 8 columns. 8 rows simply means rows simply means queries, and column simply means the keys. Okay, and right now these values are not between 0 to 1. So to make these values between 0 to 1, we will use softmax. And this is what we did next. We performed scaling and softmax. Scaling, this part over here is scaling. Guys, if you don't remember this formula, check the previous video over there. We have discussed this in detail. So basically, to perform the dot product to get the attentions score for all the tokens, so we use this formula, and I've explained step by step how to use it in my previous video. So this square root of dk over here, so this we used for scaling the values, and this q and key transpose, the values which we get over here when we multiply these two queries and keys, the values which we get, to scale those values we use the square root of dk, and dk is, what is dk? Dk is 64. How we get the 64? Because the d model is 512 and number of heads in the paper mentioned is 8. Which paper we are discussing? Attention is all you need, so you get 64. So this is how you got the 64 over here, and square root of decay is 8. And then we are applying softmax on it. Why we are applying softmax on it? Because with the help of softmax you will get the matrix like this. See, all the values are between 0 to 1. This is again a attention matrix. Which attention matrix? This is this attention matrix. Okay, but here the values are not between 0 to 1, so that's why we applied softmax. After scaling these values, we applied softmax on it so that we get the probabilities between 0 to 1, and when you'll sum up each row, so you will get sum as 1. So this is what we are doing over here. See, now all the values are scaled between 0 to 1, and when you'll sum each row, you will get 1. And after that, once you scale the values and then you used softmax on it, then we are multiplying it with value, this value. See, this is the formula. This is the formula to calculate scaled dot product attention. So we multiplied valued with it. So the size of value matrix is 8 into 64. Guys, remember, what is this 8 into 8? This is the attention matrix which we got, this attention matrix. Now this attention matrix is only related to query and key. We are not talking about value over here. So from this matrix we know that okay, this word is important for this particular word, right? This is what we know from this attention matrix. Now once you know which token is important for which query, we need to get the actual information related to that token. Means, if let's talk about this my, means, see here, this is the query of my token, this is the query of my token. Now this query of my token is checking which word should I pay attention to. And over here, this is the token with the highest value. So my token know that I need to pay more attention to this Aarohi token because the value over here is high. Now, whatever is there in the value vector of Aarohi, that part we need. Okay. So the value vector over here is giving the actual information, and the size of value vector is 8 into 64, right? Because dv is 64. So our attention matrix is 8 into 8, and we want to multiply our attention matrix with the value this over here, and the size of value matrix is this 8 into 64. Inner dimensions are matching, so we will get a matrix of size 8 into 64. Now we will have 8 rows and 64 columns. Those 64 columns are going to have some numbers in it, right? That is the actual information. That is the actual information about that token. This is the final shape of the matrix which you get after scaled dot product attention. What is the size? We got a matrix of size 8 into 64, and you know how we got this. Okay. So this is the matrix. How many values we have in it? So we have 64 values in each row. For my token, this is the vector. For name token, this is the vector, and each vector have 64 values in it. Why? Because the dv is 64. This part we have done till now. Now let's discuss what is next. Guys, let me open the paper once and let's see what is next. So see, this is what we have discussed till now. This formula you know. And the next thing is multi-head attention. This is what we are going to learn today. See, we will learn what this means, whatever is written in this section. Now we will cover that. And after that, we will also cover this position wise feed forward network. By the end of this lecture, you will know the entire working of encoder. So let's understand. So first we are starting with this multi-head attention. So first we will understand the meaning of head. So one head simply means one self attention computation. Okay. So one head is one self attention computation. And in the same way, this is also one self attention. This is another self attention task. And this is also a self attention task. Like this, all the heads are separate self attention tasks. And in the attention is all you need paper, how many heads they have used? They have used 8 heads. Okay. So guys, if you remember above here, when we calculated the dk and dv, let me show you here. So here we have used the number of heads, and I've told you that I will tell you what this head is. Now we are discussing this. So in attention is all you need paper, they have used 8 heads. And head simply means a self attention task. And the number of, if the number of heads are 8, that means 8 separate self attention tasks. And they are getting computed parallelly. And in each self attention, this task is getting performed. Which task? We are calculating query, key, and value vector for each token. So that means the process which I've explained you over here, na, exactly that same process is happening 8 times because the number of heads are 8. Okay, let's discuss this in more detail. So number of heads are 8. That means 8 times self-attention task is getting performed. That means 8 times we are calculating query, key, and value vector for each token. First, let's talk about this first head. So we performed self-attention, and after that we got a matrix of size 8 into 64. Right? This is what we got now. This matrix. Right? So in the same way, in head 2, which is another self attention operation, here also you will get a matrix of size 8 into 64. In the same way, for each head, you will get a matrix of size 8 into 64. So if attention heads are 8, that means you're going to have 8 attention matrices. Okay, you will have 8 attention matrices, and you can write it like this: head 1, head 2, up to head 8. And in each head, you are going to have a matrix of real numbers, and the size of that matrix will be 8 into 64. This is what they have mentioned in paper. If you want, we can open the paper and we can see this part once. Okay. So multi-head attention, let's just scroll down. See here. Heads, head 1 up to head h. I will tell you about this concat now. Now the next step is to concatenate these 8 matrices into one. So for that, you will use concatenate head 1 to head 8. See here, when you will perform concatenation, now what will happen? Why this 5 and 2? How we are getting this 5 and 2? Because the size of each attention matrix is 8 into 64, right? If you'll see here, the size of each attention matrix is 8 into 64. So why I have written that after concatenation, you will get 8 into 5 and 2. That means 8 rows and 5 and 2 columns. How we are getting this? Let's understand this. See, number of heads. What are the number of heads we have? Number of heads are 8, and the output of each head is 8 into 64 matrix, right? Output of each head is 8 into 64. So that's why 8 into 64, this 8 into 64 will give you 512. And the D model is also 512. Right? Remember this, we will use it in some time. So D model is also 5 and 2, and we are using number of heads 8, and the output of each head is 8 into 64 attention matrix. So that's why when we will perform concatenation, after performing the concatenation step, you will have 8 rows, because the number of tokens in our input sentence is 8, and each token will have 5 and 2 numbers in it. Okay, so we can write it like this also. See. N, I have told you what this N means. N means number of tokens. So this N is number of tokens, and this D model is 512. This is what I've told you over here. So this is the step we have performed. And guys, let's open the paper and see this section. See, so this is the multi-head attention topic. So till now, we have performed this step. We performed concatenation on all the heads. What this part is WO, this part I'll tell you in some time. Okay. So we did this part. And see here, heads is equal to 8. That is what I've told you. Number of heads we have is 8. DK, DV. How we get DK and DV? When you divide the model by number of heads 64. This part also you know. And guys, one more thing. Here we are not performing any calculation. Concatenation means we are not performing any computation over here. What we are doing is we are just placing the output of each head side by side. Okay, for each token, we will have first 64 numbers of first head, then next 64 number of second head, next 64 number of third head. Like this, we are just placing the output of each head side by side. This is what concatenation means. We are not performing any kind of computation or calculation over here. And guys, before we move further, one important detail, that the input and the output of the encoder should be of same shape. And what is the shape of input which we gave to the encoder? 8 into 512. Why 8 into 512? Remember guys, what is the input to the encoder? Input to the encoder is the vector which you got when you performed element wise addition on embedding vector of each token with the positional encoding vector of each token. And the size is 8 into 512. 512 we got because the D model is 512. Now, if input is 8 into 512, that means the output of encoder will be 8 into 512. This is the important thing to understand, that input to the encoder and the output of the encoder will be of same shape. Why? That part let's discuss now. So guys, in transformer encoder, after multi-head attention, we are using layer normalization. Okay, let me open the paper and show you first. See, after multi-head attention, we are using normalization, add and normalization. Add means element-wise addition and normalization. So the output of multi-head attention will be added with the input of the encoder, and the size of the input of the encoder is 8 into 512. And if the size of multi-head attention is something different, let's say 8 into 2046 or 8 into 315, whatever, right, then what will happen? Then you cannot perform element wise addition. Okay, so just see here, this is the formula. When you want to perform layer normalization, what we do is attention output. What is the attention output? This output, output of the encoder. Okay, and this x is the input of the encoder, input of encoder, which we got after performing positional encoding and embedding vector element wise addition. So we want to add this with the output which we got after the attention task. And if this size is different than 8 into 512, then we cannot perform the addition on it. Okay, so that's why it is mandatory that the input of the encoder and the output of the encoder should be of same size. Now over here, the x matrix is of shape 8 into 512, and attention output is also 8 into 512. Okay, now we can perform element wise addition on it. So guys, that's why the shape should be same. And guys, it's not about this only. Inside encoder, each sublayer will have the same shape. Remember this. If the input is 8 into 512, then each sublayer of the encoder will give you an output of same shape 8 into 512. So now let's understand the next step of encoder, which is linear projection. But till now, what we have done, we have 8 heads. 8 head means 8 self attention which are running parallelly, and the each head output shape is 8 into 64, and then we performed concatenation on all the 8 heads. So we got the output matrix of shape 8 into 512, right? 8 tokens we have now and 512 columns, and these columns are just combined features from all the heads. So guys, as I've told you that next step is linear projection, but why we want the next step to be linear projection? Because we have performed concatenation over here, and concatenation simply means placing each head's output side by side, and these heads, they do not talk to each other, and we need something which learns that which head matters for which feature. And for that we need one weight matrix wo. So guys, remember the paper. Let me go to the section, multi-head attention section here. So we know what this concat is, what this head 1 to head h is. Head 1 to head h simply means the number of heads. So we have 8 heads. We perform the concatenation, and then we are using this weight matrix wo. Now we are going to talk about it. Why we are talking about it? Why? Because we are performing the linear projection. And why we are performing the linear projection? Because when we perform the concatenation, we placed everything together, but which head is important for which particular feature, we don't know that. So we want to teach that to the model. So for that we are using this weight matrix. So this weight matrix will combine information across all heads. It will learn which head matters for which feature. Here, let's discuss it. See, so this is wo weight matrix which we will use now, and input features into weights and you will get the output features. So what is this input feature? Input feature is the output which you get after concatenation. So what we got after concatenation? Okay, let's go back. This is what we got after concatenation. So this is the input feature. What is the input feature? Let's write it over here. So the input feature is the matrix of shape 8 into 512. And what is this weights? This weight is the this weight matrix, this W, which we are going to learn. And this will give you the output. Okay. And guys, this weight matrix will be of size 512. How, why, that part we will discuss. Okay. So we know that the input features is a matrix of size 8 into 512. And we don't know what this weight matrix is right now. Okay, so question mark. But the output, we know what kind of output we want. We know that the shape of the output will be 8 into 512 because the input to the encoder and the output of the encoder will be same. And I've also told you that in every encoder, each sublayer will give you the same shape. We know that the output shape of this will be 8 into 512. Suppose M is 8. 8 means number of tokens, right? N is 512 means number of input features, and P is output features, number of output features. So output features we want is 512, input feature we have is 512, and number of tokens we have is 8. And if you'll apply the matrix multiplication rule, so that means if you have a matrix A which have shape M into N, and you have another matrix of shape N into P, you will get a M into P, right? So that means 8 into 512, this is our first matrix, input matrix. This 512 into 512 is our weight matrix, this weight matrix which we want to learn, and inner dimensions are matching, and you will get a matrix of shape 8 into 512. And this is what we want, right? We want a matrix of shape 8 into 512 because the input to encoder is a matrix of shape 8 into 512, and each sublayer of encoder must produce output shape of same size. And guys, why we are using this weight matrix over here? Why we are using this linear projection? Because it will combine the information from all the 8 heads into a single 512 dimensional vector for each token, right? For each token, we are going to have a vector of size 512, and that vector will have the information from all the 8 heads, means all the 8 self-attention tasks which are performed. We are going to have the information from that into single vector, and the shape and the size of that vector will be 5 and 2. For one token, we are going to have 5 and 2 numbers now. Guys, what will happen? Suppose if we are not performing this linear projection task over here, then what will happen? Then all the 8 heads will not interact with each other. The information which they have, they cannot share with each other, right? So we use this weight matrix so that all the information from all the self-attentions mechanisms can be combined together into a one-dimensional vector for each token. So till now, what we have done, this is the input to the encoder. Then we calculated query key value. Then we used 8 attention heads. Then we concatenated their result. After concatenation, we have a matrix of size 8 into 512. Then we performed linear projection on it. After linear projection also, what is the size? 8 into 512, right? Now, the next step is to perform add and normalization. So we will perform. So now, in this step, we will perform element-wise addition on this and on this matrix which we got after this linear projection. Okay, so we will perform element-wise addition between them, and the size, the shape is same, so we can easily do that. Which formula we are going to use? So guys, I've shared this formula over here. So this formula, X means the input of the encoder and the attention output. You will perform element wise addition on it, and then you'll perform normalization on it, and you will get the output. Here you will get the output. That output will become the input to the feed forward network. This is what we are going to understand now. So guys, this is the part which we are going to discuss now. And this is the formula which I'll explain you in some time. What is the meaning of this position wise? Everything I'll explain you. Okay, so let's start. So feed forward network will have 3 layers: linear layer, ReLU layer, and linear layer. And this is the formula which we have seen in the paper. See this. Now let's understand this. So this part, this much part, this is the first linear layer. This part is the second linear layer. And this ReLU is over here, max 0, and whatever the output we get over here, and we will apply ReLU on it. Okay, so this is how this feed forward will work. This formula which you're seeing over here is a combination of 3 tasks: first linear layer, then ReLU layer, and then linear layer. Let me explain you one by one how we are going to work on it. So the input to this feed forward network is the output from the previous layer, which is 8 into 5 and 2 size matrix, right? See, 8 into 5 and 2. This will become the input to the next layer. So the first layer, what I've told you, what is there in the first layer? This much part. X means input into weight matrix plus bias. So weight 1 is the matrix for the first linear layer. Weight 2 is the weight matrix for the second linear layer. This bias 1 is the bias which we will add, which we will use in the first linear layer, and this B2 is the bias which we will use in the second linear layer. Okay, and this X is the input, and you know that X is a matrix of size 8 into 5 and 2. So see here, they have mentioned 2048 over here. So what it is, let's understand. So the first linear layer will take the input of shape 8 into 5 and 2, which is the output of the previous layer, and it will project it to 8 into 2048. This means that each token is now represented by a 2048 features. Why we increase the number of features? Because it will allow the model to perform more richer and more expressive transformations on each token. It will understand the token in more detail then. And guys, see over here they have mentioned position wise. What it means? Position wise means that it works on each token independently and it does not mix information between the tokens. What will be the output of this linear layer then? You will get output, you will get a matrix of shape 8 into 2048. How? This is how we get this. Okay. Now that output will become the input to the ReLU activation function. ReLU activation function will add non-linearity to it. It will make all the negative values to 0. And then finally we have the second linear layer, which is this. Means W2 plus B2. B2 is bias and this W2 is weight matrix of this layer. Now guys, remember I have told you that each sublayer of encoder will produce the output of shape 8 into 5 and 2 because encoder output should be of shape 8 into 5 and 2. Why? Because the input of encoder is of shape 8 into 5 and 2 and the input and the output of the encoder should be of same shape. So now the second linear layer will again make the matrix 8 into 5 and 2. See guys, the input to the first linear layer, what is the input to this first linear layer? The matrix of shape 8 into 5 and 2. But this linear layer projected it to 8 into 2048 because it want to have the deeper understanding of the tokens. And then the input to the ReLU is this matrix. Now ReLU activation function added non-linearity to it. It converted all the negative values to 0. And then the input to this second linear layer is a matrix of shape 8 into 2048. But remember, this layer should produce an output of size 8 into 5 and 2. Why? Because the input of encoder is 8 into 5 and 2. And each sublayer of encoder should produce the same shape because then only you're going to have the output shape of encoder as 8 into 5 and 2. So that means this second linear layer will again make it 8 into 5 and 2 matrix. Okay. So the second linear layer will project the representation back from 2048 dimension to 512 dimension so that the output shape matches with the encoder input and it can be used with the residual connections. Now guys, understand one thing. The attention which we calculated before this feed forward network, that attention tells a token what to look at. And this feed forward network, what it learns, it tells the token how to process what it has learned. Okay, so mathematically this is what it means, and this is the final matrix you get from feed forward network of size 8 into 5 and 2. So this is the same shape as input. So now you can give it to residual connection. So guys, now the work of one encoder is finished. Let's open the paper and see. So guys, now the work of one encoder is finished. Now let's open the paper and see it. This is the working of one encoder. In the same way, we will work for other encoder, because in attention is all you need. They have mentioned 6 encoders and 6 decoders. So they are stacked one after the other. The output of the first encoder will become the input to the second encoder. The output of the second encoder will become the input to the third encoder. Like this, it will work, and the output of the 6th encoder will be the final encoder's output, and after that we will give it to the decoder. That part we will discuss in the next video, and that's it for today. So I hope this video is helpful, and guys, if you like my content, please like, share and subscribe my channel. Thank you for watching.